So, greetings of the day, students. In last lecture, we have discussed about two different micro operations. The one is called serial, and the another one is called parallel, right? So today we will learn few more categories of micro operations: register transfer micro operation, arithmetic micro operation, logic micro operation, and shift micro operation. So let's start with the discussion. So in last lecture, we have also covered this arithmetic micro operation. Today, I am going to explain you the logic micro operation. So first of all, it specifies the binary operation on the strings of bit registers. So logic micro operations are basically bitwise operations. What does this mean? Bitwise, it means it will work on individual bits of the registers. Right? For example, you have 8 bits of register, 0, 1, 1, 0, 0, 0, 1, 1. Right? So are you able to see the whiteboard?
Yes, sir.
Yes, sir. Okay, good. So here you can see that these are your bits, right? So all your logic micro operations will be performed upon individual bits, right? So these are useful for bit manipulation on binary data. It means you are going to perform all your logic micro operations on the binary data, which means 0 or 1, right? Which means 0 or 1. Next we have just hold on. So it is useful for making logical decisions based on the bit value, right? So we have 4 categories of logic micro operations. The first one is called AND, which will be written with the help of this symbol. Then we have OR, logic micro operation, which will be written with the help of this symbol. This is for and this one is for OR, right? Next we have XOR operation. For XOR, we are using this symbol. Last but not the least, we have complement. We have complement slash note micro operation, which will be written with dash, or you can write it as a bar, right? So let's discuss all the operations, logic micro operations, one by one. So here you can see on right hand side, I have listed some micro operations which falls under the category of logic micro operations, right? So first of all, first name is clear. So it means you will need to clear all the bit values of your register, right? Next we have A and B. So let's take some examples. So here logic micro operations can be used to manipulate individual bits. Let me show you some live examples for the operations. So first operation is AND operation, right? So how the values of two registers will change. For example, we have A register and we have B register, and both the registers are of 4 bits each, right? So for AND, we have this sign, right? So what will be the truth table for AND? Let's have a look. For 0 0 it is 0. For 0 1 it is 0. For 1 0 again it is 0, and for 1 1 it will be 1, right? So this is the truth table for and you have to apply these operations upon your individual bits, right? So first of all, let's take 1001. So this is the value for A register, and for B we have 0101, right? Now you are going to perform and logic micro operations, right? So you just need to check from your table, right? So here 1 1, here 1 1 is 1, right? So here 1 1 is 1, so here you will get 1. For 0 0 you have this 0. For 0 1, for 0 1 you have 0, and for 1 0 again you have 0, right? So this will be your answer, which will be stored again in A, right? So it will imply A and B. There will be a AND micro operation which will be performed between A register and B register, and your answer will be stored into A register as well, right? So similarly, you can perform OR micro operation. OR micro operation. So first of all, you need to know the truth table for OR. So for OR micro operation, you have A register, B register 0 0 0 1 1 0 1 1, right? So for 0 0 you will have 0. For 0 1 you have 1. For 1 0 again you have 1, and for 1 1 you have 1.
0.
So this will be the truth table for OR logic micro operation, right? So again, the values of A and B are same, right? But you have to apply the OR micro operation between these two registers, right? So first of all, for these 1 1, for 1 1 the answer will be 1. For 0 0 it will be 0, and for 0 1, 0 1 means 1, 1 0 means 1. So this will be the answer after performing OR logic micro operation, right? So similarly, we have XOR. XOR means how you will get XOR gate simply by negating the output of OR, right? So it will be written as the truth table will be A XOR B. So here the output will be true only if the either value of A and B is 1, right? How you will get the true output, how you will get 1 as an output? You should have one true value either in A or in B. It means 0 0 it is 0. For 1 1 again it is 0. For 1 0 it will be 1, and for 0 1 it will be 1. So this is your XOR gate, right? So this is your XOR gate. So let's apply operation upon A and B. For example, you have 0, 0, 1, 0, 1, 1, 0, 1, right? So A and B registers are of 4 bits each. So here you need to apply the XOR. So what you will get
1111.
here, you will get 1, 1, 1, 1. Very good. So all 4 consecutive ones you will get after performing XOR. And last operation is clear or complement. Clear or complement or not. Clear is something different. So for complement and not operation, you will have only one register. So here your value is 0, 0, 1, 0. So after performing this note, your values will be 1, 1, 0, 1.
01.
Right? You just need to negate your values. If there will be 0, it will be 1. If there will be 0, it will be 1. If there will be 1, it will become 0. Right?
Sir, your voice very low, sir.
Voice is low.
Yes, sir.
Now,
No, sir.
hello.
Yes, sir.
Audible?
No. Yes.
काफी लो है सर.
सर क्लियर है.
तो ठीक है सर.
So next we have logic microoperations can be used to manipulate individual bits or a portion of word in a register. Consider the data in a register A, right? And another register will be B. So is the bit data that will be used to modify the contents of A, right? So here we have 3 basic applications of this logic microoperation. Let's discuss it one by one. So first of all, we have selective set. Selective set operation. Right? So what does it mean? So it sets the bits on register A to 1. Kindly read this definition very carefully. It sets the bits on register A to 1 where there are ones in the corresponding bit of register B. Right? It means set means it will make the bit to 1, right? So I am writing the example on the blackboard. That is 1, 0, 0, 1, 1, 0, 1, 0, right? So this is your register A and this is your register B. You just need to see on B register and set the corresponding value of A register and write your answer here. What you have to do, it sets the bits on register A to 1 where there are ones in the corresponding bits of B, right? So what it does, you need to find the 1 values in B. So here you will have 1. So the opposite bit of A is already 1. So you need not change it. Right? This will becomes 1. Then you have 0. Now here again you need to find one more 1. So the bit corresponding to B is 0. So here you need to set this bit to 1. And for 0 it will remain same. I hope the concept is clear. Right?
Yes.
Let's take one more example. So here 0, 0, 1, 0, 1, 1, 0, 1, right? So this is your A and this is your B. Selective set operation. As the name suggests, selective set, which means that you have to check the bits of B and set the corresponding bits of A where there will be 1 in B. So here there is 1, but the bit in A is 0. The answer will be 1. Again, here is 1, but the bit in A is 0. Again, the answer will be 1. For 0, it will remain same. For 0, it will remain same. That is 1. Again, for 1, the bit corresponding to A is 0. Again, there will be 1. So this is your answer. So this is your selective set operation, right? Set. Next operation we have selective complement. Selective complement. Again, it complement bits in A. Here there are corresponding ones in register B. It does not affect the bit positions that have zeros in B, right? It is similar to exclusive OR gate. So let's see the example. So here you have 1 0 1 0 1 1 0 0. So we have two registers. So again here you need to apply, that is selective. The operation is selective complement, right? Selective complement. So here the operation is selective complement, right? Again you need to check the bit for B and complement the corresponding bit of A. So here you will have 1 and 1, right? So the corresponding bit of this one is 1. So it will be 0. Its complement, that is 0. Again here 1 in B at this position and the corresponding bit is 0. And you need to complement it, right? And for 0, the bits in A will remain same, right? So you don't alter the bit values which are having 0 in B, right? You need to change those values of A where there will be a corresponding ones in B, right? I hope the concept is clear.
Yes.
Yes, sir.
One more example is 0 0 1 1. 0 1 0 1, right? So here 0 0 for 0 0 it will remain same bit. For 1 you will have to complement the bit in A, so it will be 1. Again for 0 the bit value will remain same, that is 1. And again for this one it will be
0.
complement, so your answer will be 0 1 1 0, right? So next we have the third operation, that is selective clear. So this operation clears to 0 the bits in A only where there are corresponding ones in B, right? So this time you need to clear the values, right? So let's check. So here selective clear means you will have to make the bits to 0, right? So here is 1. So the opposite value of 1 is 1 will be 1. So you will make it 0. You have to clear it. Again for this it is already 0, 0. And for 0 the bit value will remain same, right? So this will be the answer. The second example is, this is second example, this is first example. Again for 0, 0 it will remain 0. For 1, 0 the bit is already cleared, so 0. For 0 it will remain same, and for this one the answer will be 0, right? So these are the applications of logic micro operation.
सर सेकंड वाले को फिर से बता, सेलेक्टिव क्लियर का, सेलेक्टिव क्लियर एक बार और बता दीजिए.
So here you will have to clear those values of A where there will be 1 in B. So here you will find that we have 2 ones at second location and fourth location, and you will have to make the opposite bit to 0 only, right? So for 0 no change. For 0 it will be 0, that is as such bit. For this one it is already 0, so 0 will be copied here. For this 0 the same bit will be written, that is 1. You need not to change the bit value of A where there is 0 in B, right? For this one again you have to clear it. So this is your answer, 0, 0, 1, 0. So next category is shift micro operations. Next category is shift. So these are used for serial transfer of data. Serial transfer means the bit values will be taken to the next flip flop, right? For example, you have 4 bits of register, 0, 1, 1, 0. So this is your 4 bit of register. So what does shift means? Either your bits will be shifted to right hand side or it will be shifted to left hand side, right? So shift will be of 2 categories. The one is called left hand side and the another one is called right shift, right? So you just need to transfer your bits to next flip flop, right? When a new value will be inserted from this side or either it will be inserted from this side. So let's see it in the later on section. So that means we can shift the contents of register to the left or right. What differentiates them is the information that goes into the serial input, right? So there are 3 types of shift. The first one is called logical shift. The second category is called circular shift, and the third category is called arithmetic shift. Logical shift, circular shift, arithmetic shift, right? So let's proceed to logical shift. So see these 2 diagrams very carefully. So first of all, in a logical shift, the serial input to the shift is 0. Remember this point. You will always take 0 as a serial input, right? And you have to shift your values according to the shift. So for right logical shift operation, all your data will be shifted to right hand side. So this is your right hand side and this is your left hand side, right? A 0 will be inserted from left side and all the other bits will be shifted to one position to the right side. I hope the concept is clear. For left logical shift operation, the 0 value will be inserted from right side and all the other bit values are shifted to left hand side. as the name says, right? So we have two categories of logical shift operation. The one is called SHL and the another one is called SHR. SHL, SHR. So suppose you are going to perform your write logical shift to R2 register. So it will be denoted with SHR. Similarly, for SHL, your register is R3. So SHL means left logical shift, right logical shift. So let's proceed towards the numerical example for this. So we have right logical shift and left logical shift. So I will make you clear by taking suitable examples for it. For example, so here is your 5 bits of register 0 1 0 1 1, right? So first of all, I'm going to perform the right logical shift, that is SHR. So this time all a value, that is a 0 will be inserted from the left hand side. So this is my left hand side and this is your right hand side, right? So this is before shift, and what will be the answer? This is answer after this, right? So 0 will be inserted to this flip flop and all the other values will be shifted to 1 bit to the next level, right? So you will get 0. This 0 will be taken into this place, that is your first place, and this 0 will be taken to next position 0. Then you have 0 1 0 1 and this 1 will be closed. So this is your right logic shift, right logical shift, right? Similarly, if you need to perform left SHL, SHL means this before. Now this time a 0 will be inserted from right hand side and all the other bit values will be shifted to left position. That is, it will be moved to this will be moved to this, it will be moved to this position and it will be taken to outside. So after the left logical shift, your answer will be this 0 will be taken into this position. So it will become 0 1 1 0 1 and this 0 will be closed. So this is after performing left logical shift. Next we have circular. Next we have the second category, which is called the circular. So The objectives of this PPT will be, so you should be able to learn about the difference between left circular shift and right circular shift, learn how operations are performed in ALSU with the help of table, and understand how overflow is detected in arithmetic left shift. Right? Let's proceed. So next we have circular shifts. So here circular shift, which is also called rotate operation, it circulates the bits of register around the two ends without the loss of information. You have seen that in case of logical shift, right? Whether it is left logical shift or it is right logical shift, in both the cases, your value will be lost, right? But in case of right circular shift, all the values will be rotated to another end. So there will be no loss of information, either in case of right circular shift or in case of left circular shift, right? So for right circular shift, all the values have been shifted to right side and your last value will become the first value. Similarly, in case of left circular shift operation, all the values will be shifted to left side. All the values will be shifted to left side and your first value becomes the last value, right? So the circular shift will be denoted with the CIL or CIR. So for right circular shift, you will write CIR, then the name of the register, and after performing the operation, it will be stored into R2 again. And similarly for left circular shift, it is CIL R3, then you have R3, right? So let's take one example for this. So taking the example of right circular shift, right circular shift. So here you have, let's suppose your register is of 5 bits, again 1, 2, 3, 4 and 5, and the values are 1, 0, 1, 1, 0, right? So this is your right circular shift. It means all the bits will be shifted circularly to the right hand side, to this side, this side, this side, and so on, and the last value becomes the first value. So before the shift, your data is 10110, right? And after performing the shift, it becomes this zero will be taking to the first position, that is this zero will be taking to the this position, and all the other will be shifted to next, next, next. I hope the concept is clear.
Yes, sir.
Check again, this zero will be taken outside and it will move to the first position, so it will become 0, and all the other bits will be shifted to next flip flop. So it will be going to this position, this position, this position, this position, and this 0 will be taking to hold the first position. So this is your right circular shift. Next we have left circular shift. For left circular shift, Again, suppose you have 5 bits of data in your register 11101, right? So you can take any example of your choice. So after performing this time, because this is your left circular shift, all the values will be shifted to left hand side, right? So this, all the bits will be shifted to left hand side, and this first will be taking place to the this position, right? So let's see. So this one, first of all the bits will be shifted to left hand side. So here you will get 1 1 0 1 1. I hope the concept is clear. Left circular shift, right? So all the bit values will be shifted to left hand side, and this shift will be moved circularly to by taking the first position, and your answer will be 11011, right? So this is about your left circular shift and right circular shift. Next we have arithmetic shift. So this is very important shift. So see it very carefully. So an arithmetic shift is meant for signed binary number, that is the integers. Signed binary number means there will be one sign. For example, I have written -10, -10 or +10. So this is your signed number, right? Whenever you are going to play a sign before your number, it is your signed number, right? And an arithmetic shift is meant for signed binary number. So you need to convert this decimal number, that is 10. 10 is 10. So this is your decimal number. How you are going to convert this decimal number into binary number? By with the help of 8421 formula, right? So here you have, by making 8 plus 2, that is 10. So 1010. How you can make it 5 digit? By placing a 0 before the number, right? 01010. So this is your signed binary number, right? Clear hai?
Yes, sir.
Very good. So how this arithmetic shift will work? Let's see. So it shifts a signed binary number to the left or right. An arithmetic shift left multiplies a signed binary number by 2. We will take the example for it in later on section. An arithmetic shift right divides the number by 2, right? So the leftmost bit in a register holds the sign bit. If your register will be of 5 bits, if your register will be of 5 bits, these 4 bits will be used for holding the number, and this
Sign.
left bit will be used for sign bit, right? For example, we have taken example of -10. So for binary 10, in binary you can write 1010. So this first will be used for sign, and for minus you will always use 1. For minus the bit value will be 1, and for plus it will be 0. So this is your sign, right? If I am saying you have 8 bit of register, right? Now how you gonna represent your 8 bit value? So 0 1 0, 1, right? 7 bits will be used for storing your number, and the last one will be used for storing the
Sign.
sign bit. So this is your minus 10 in 8-bit representation. Minus 10 in 8-bit representation for my minus, you are having this 1 as a sign bit, right? So a right arithmetic shift operation. So let's understand it, and then we will be understanding these 2 points, how the bits are multiplied by 2 in case of arithmetic shift left, and how the number is going to multiply by divide by 2 in case of shift right operation. So first of all, let's understand ASHR. ASHR is used for arithmetic shift right operation. Similarly, ASHL is used for arithmetic shift left operation, right? So let's see. So let's suppose again you have 5 bits of data. Because the shift is right, it means all the values will be shifted to right side, and the first value will be of your sign bit. So what does this mean? ASHR, right? So this is your 5 bits of register. Suppose the value is uh, plus 12. So how you are going to write plus 12?
1100.
So you have 1100, and for plus your 5th bit will be 1. So it will become,
Sir, for plus it will be 0.
जीरो नहीं होगी
it will be 0. It will be 0. Very good. So here you have 0, 1, 1, 0, 0. Now you are going to perform the ASHR, right? So first of all, this 0 will be taking into the position of 0, and again it will be shifted to next as well. So what will be your answer after the shift? The 0 will be taken to this position. After the shift, this 0 will be taken place to the next position. Again a 0 over here. Then you have a 1 over here. Again you have a 1 over here, and a 0 will be there. And this last 0 will be closed. The last 0 will be closed. Right?
सर एक और एग्जांपल लीजिएगा
Just wait जाओ.
सर जिसमें माइनस हो
लीजिए. So taking the example of 14 or
माइनस 14
minus 14, right? For minus 14, what will be the value? First of all, you need to calculate the values.
1110
According to 8421, how it becomes 14?
1110
1110, right? And for minus 14, the first value will be 1110. So this is your minus 14 representation in. This is your minus 14 representation in binary.
yes sir clear
Find binary number, right? So
Yes.
after performing the shift, so this one will be taking the place of 1, and it will be moved to next position. So what will be your answer? 1 1 1 1 1, and last 0 will be closed, right? Last 0 will be closed.
yes sir
I hope the concept is clear.
yes sir clear
So this is your ASHR. So 4 plus 10. This is your 0, 1, 0, 1, 0. And after performing the shift, it will become 0, 0, 1, 0, 1, right? So I'm going to show you the concept of how the number will be multiplied by 2. An arithmetic shift right divides the number by 2, right? So let's see. So here you can see that plus 10 is 0, 1, 0, 1, 0, right? So this is your before the shift and this is after the shift. So you can see that 101 is plus 5. So you can see clearly that your number is divided by 2 after performing the ASHR. I hope the concept is clear. An arithmetic shift right divides the number by 2. So let's proceed toward a left arithmetic shift operation. A left arithmetic, that is your ASHL. ASHL, right? Now for this, a 0 will be inserted from left hand side, and in this case your sign bit will be closed. In case of, you can see the diagram in front of you in PPT. So your sign bit will be lost in case of left arithmetic shift operation, and a 0 will be inserted. So let's see the example. Again it is for 10 and for 5 bits it will be a 0 will be inserted from this side. And let's see the example for plus 10. For plus 10, again here this value will be 0, 1, 0, 1, 0, right? So this is your sign bit. So after the ASHL, so this 0 will be inserted into this position. So what you will get, your 5 bits of register will be changed to a 0 will be inserted to this position. This 0 will be moved to this position, 0. Then you have 1, then you have 0, then you have 1, right? And this 0 will be closed. Now you can convert it into 16, 8, 4, 2, 1. So 1, 0, 1, 0, 0. So this is your 20. So we have started with 10 value, but after performing the ASHL, your value becomes twice. It means that an arithmetic shift left multiplies a signed binary number by 2. I hope the concept is clear,
Sir,
right?
Yes.
So how the concept of this sign reversal has been achieved, let's see with the help of a diagram. So here you can see that the bits are represented with Rn minus 1, Rn minus 2, and so on up to R1, R2, right? So this is your arithmetic shift right operation. We have already discussed it. Next we have arithmetic shift left operation, arithmetic shift, right? So here the arithmetic shift left inserts a 0 into the R0 position. So this is your R0 position, R1, R2, and so on up to Rn minus 2, Rn minus. This is your Rn minus 2. This is your Rn minus 1. So according to this, right? Rn minus 1, Rn minus 2. So here it says that the initial bit of Rn minus 1 is lost and replaced by the bit from Rn minus 2. So we have seen that this is your Rn minus 2. This is our Rn minus 1. So here Rn minus 1. So this is your Rn minus 1 is lost and it will be replaced with Rn minus 2. Right? So this statement is true. So an overflow occurs after an arithmetic shift left if initially before the shift Rn minus 1 is not equal to Rn minus 2. Let's understand this. So it says that this is your Rn minus 1 bit, this is your Rn minus 2 bit. It says that an overflow will occur if these two bits are not same, right? How it occurs? So here you can see the diagram. An overflow flip-flop V can be used to detect an arithmetic shift left overflow, right? So we are going to attach one XOR gate to these last two 1 and 2 bits, right? So here you have V. So as you know that what your XOR gate will do, XOR gate is 0 0. For 0 0 it is 0, for 0 1 it is 1, and for 1 0 it is 1, and for 1 1 it is 0. So this is your XOR gate. So if these two bits are not same, you will always get, if these two bits are not same, you will always get an overflow in V. I hope the concept is clear. If V is equals to 0, there is no overflow. If V is equals to 1, there will be an overflow. So there will be always a sign reversal after the shift. So these are the summary of various shift micro operations. So first two corresponds to logical shift. SHL means logical shift left. SHR means logical shift right. CIL means circular shift left, and CIR means circular shift right. Similarly, ASHL means arithmetic shift left. Similarly, ASHR means arithmetic shift right. So thank you.